Right, so now we have Aziz Kharoof from the University of Haifa talking about homotopical characterization of strong contextuality.
Thank you very much. Hi, everyone. Thank you for the organizer. So let me start, okay. I want to start with the experiment in a quantum physics, actually. In quantum physics, sometimes we have something like this, like we have some system here, we're doing some experiment together. We don't understand here what happens, but we know that there is two results, for example, for every experiment. Let's say that's 0 and 1, okay? And we do this experiment together and get the results. So sometimes it's happened like this, that we can't, for some reason, we can't measure all of them. We can measure only 2 of them. Like we decide to measure A and B. This is what we can know. Even though we do the 3 experiments together, there is a result for 3 of them. But for some physical reason, we can't know what is the result of 3 of them. We can know just 2 of them. We decide which 2. But the good news is that we can repeat it as much as we want. Okay, we can repeat these experiments as much as we want. So we can, for example, repeat it many times and every time measure A and B. Okay, what is the result of A and B? And then get a probability table for A and B. So we can get this table, right? Like probability table for A and B, for B and C, for A and C. Like, for example, what it means is Q01. It means the probability to get 0 for B and 1 for C when we measure B and C, okay? So what we expect from this probability table, of course, the sum here 1 and here all the sums 1, but it's also related because we see like A appear here and they appear here. So if I want, for example, to know the probability that we get 0 if we measure A, so we can sum this, right? Where A is 0. We can sum both of this, but we can go here and sum both of this, right? Because A appear here. So actually, this is related by this equation. Okay, and this is fact, yeah, this is true in this kind of experiment. So the other things maybe one can expect it because we said before that we did the 3 experiments together, right? So one can expect that there is a probability table for ABC, right? Like this. Right? We can expect that there is a probability table like this, but we don't have because actually we can't measure 3 of them. But there is a result. Every time we're doing this experiment together, there is a result for 3 of them. We can't know what is the result. So one can expect that there is some table like this that induce these tables. Like if I sum both of this give me AB00, it's give me this one, BP00. But it's not the case, actually. Okay, this is not the case, and there is this what actually one of the weird phenomena in quantum physics that it's happen in some experience that it can be something like this, that it's not coming from such a global probability table. Okay, something.
No, just go on.
Okay, so in this case, actually, we call this table contextual table. Okay. This is a phenomenon of contextuality, contextual table we call it. Anyway, let's give its topological description. What we did, we can actually the same experiment. What we did actually every experiment is a vertex, and every experiment that we can do together, we can measure together. Sorry, can measure, not do. We do 3 of them, but we can measure together. We put an edge, okay. And what we have actually, we have probability table for this edge, like which probability table corresponding to AB, the same for AC, for BC, for AC. And as we say, it's much here, it's compatible, right? As we say, like if we sum this, it's sum of this, depends on the direction, don't worry about this. Here the equation is exactly one of the equations that I wrote before, okay? So this can remind us the scenario, what happened, right? This picture. But actually what we want, alternative way to describe is using diagrams. We can, actually the information we have here is this. So let me explain this. Here D is a distribution monad, okay? D is a distribution monad. So actually what we have here, we have a map from 3 edges to this, right? Like 3, we have 3 elements here, right? This one, this one, this one. And such here we have two square, one for D0 and one for D1. D0, I mean D0, for example, for this is B, no? Which D0 when I omit this, so this is the direction, so it's B. Like if I take D0 of this, and then I take the probability corresponding, because there is a probability corresponding to A, which is here. This is the same as to take the distribution, this one, and then to apply, so let me explain what I mean by D of D0. D0, actually, it's by omitting the zero place, the map from Z2 cross Z2 to Z2, and we apply the functor, D, the distribution functor. So one can check that if we apply P1 and we get this, okay, for this edge, and then we apply D0, it's exactly this operation, like to sum these ones, okay? So we can encode the equations above, these equations above, using the diagram, okay? This equation using this diagram. Okay, so actually what we have, we won't actually generalize this in order to give a general definition, but let's take a look what we have here. Actually, what we have here, it's in the left, it's a description, like combinatorial description for this topological space, the easy topological space, this simple, the triangle, right? So this is simplicial set, actually, what we have here, right? So, and we here apply D on some other simplicial set. So let me remind you the definition of simplicial set. So simplicial set is a way, like, okay, this is already in the previous talk, but so we have a collection of sets, like this is the set of vertices, this is the set of edges, this is the set of triangle, and so on. And we have face maps and that tell me how it's gluing together, because it's represented some topological space. We have also degeneracy maps. For someone who don't know simplicial sets, ignores this. We not it's important for the theory. We will use the theory of simplicial sets, so it's important, but one can ignore for this talk. Okay, what is degeneracy map? So this is the simplicial sets, and the map between simplicial sets, of course, it's like okay, it explains this as a natural map, but we can say like it's a map, it's a collection of map for the vertices, for the edges that actually respect the face maps. Okay, one example, important example for this talk, this one, this simplicial set. This simplicial set is this is the vertices here, this is the edges, this is, and the faces map is by deleting. Like here we have two faces maps by deleting the first one, deleting the, as we explained before. And now we can give a definition for this table, like general definition using simplicial sets. So simplicial distribution, which generalize the tables. Simplicial distribution is actually just a simplicial map from some simplicial sets to D of delta Z. Okay, where this is Z. Because it can be any end, like it can be any outcome for the major for the experiment, right? Not just two. Okay, so this is the definition that generalize the table above. Here X is called measurement space because it's like tell me which ones I can measure together, like the triangle. Yeah, but also here the outcomes become space. Also become like, I mean space, when I say space, I mean simplicial sets, but because it's like topological space, okay? So we will back to this point. Okay, so now I want to define what is strong conceptuality. So if we fix actually a measurement space, so all the simplicial distribution, if we take all the simplicial distribution for fixed, some fixed measurement space, it's form a polytope, okay? The shape of one can see, like if we come back to these tables, like we can take two different tables, convex combination of them. It's give me also tables that have this equation. So it's form, of course, here X have to be finitely generated and things like this. This actually polytope, it's hard to explain. Even in our example, it's higher dimensional polytope, so we can't like draw here, but I actually draw the picture that can illustrate. It's not real picture, but it can explain what happened here. So this is a polytope of all the simplicial distribution, all such a table. So here we have the ones that coming from some global table. okay? Some global distribution, which is a non-conceptual, okay? Classic distributions that not come. And here's a conceptual one. And we interested in this to characterize in this one, what is it, what we mean by this? This is conceptual, but it's strongly conceptual because it's not involve any classic ones here from the idea. It's like if I have a point here, I can write it as a convex combination between two distributions that involve one from here, right? But for example, if I take this point, I can like this, the convex combination of this point with this point, for example. Okay, so this is called strongly conceptual. It's not involve any classic distribution. Okay, the simplest example that we can talk about when we have this phenomena of strongly conceptual is when we have the measurement space is just a circle with one edge, okay? This is not coming from some physical experience, of course, like as we described before, but it's part of the theory, part of the definition. What I give the definition here, it can be that X is any simplicial set. So it can be this simple simplicial set, which is just one edge with the same labels. It's a circle, okay? With this, in this case, we can actually draw the real polytope. So this is the polytope. So it will be like polytope like this, where here everything is a conceptual distribution. We have this line, it's with classic distribution, non-conceptual distribution, and we have unique, strongly conceptual distribution or vertex. It's in this case, okay? In this case, we will back to this. We will use this later, even if this is not coming from some experiment, but we will back to this later. Okay, so let me now back to the definition of simplicial distribution. Actually, there are many approaches for this phenomenon in physics, but what is the benefit that we can get from this approach? That it's not just the measurement space. It's have like a simplicial set. It's have some topological description. Also here the outcome. Like instead of B number, now it's a space. It's simplicial sets even. And the simplicial sets is a tool, it's an important tool in homotopy theory and in category theory, in both. So we now show how we can get the benefit from seeing this as a topological space and the homotopy rule of this, and also seeing this as in point of view of category. Okay, we will see. First of all, let's start from the topological point of view. So what is this delta Zn? Actually, this one is the set of path of the nerve of Zn that start from at some fixed point. If we have a topological space, there is a path. We can build another space, the path spaces of this that start with some fixed point. Okay, so this is the relation between this and the nerve of Zn. So we have such a map that send every path to the terminal point, okay? And using this, we can define homotopy using maps that lifting. So let me define it. There is a picture that can explain everything. Like we see that a map phi from X to nerve of Zn, map from phi to the nerve of Zn, this is null homotopic if it lifts through this. If it's lifts through this. Why? Because in this case, like we have, like for every point here is the image, we have a line, what I call it, it's a path, yeah. We have a path like that in this image, right? But they start with same point. So actually what we get, you can see in the picture, that this map, phi, is in continuous way, it's the same as the constant map, right? Yeah, so we can use this. So we can. It's actually contractible. So what I mean, it's contractible, and some map that coming through this is null homotopy. So from this observation, actually, we get the following result. So that related. This is the result. Actually, that related homotopy with strongly conceptual. So what we saying here? We're saying that if we have such simplicial distribution here, like table, like what we had before, And if for some restriction here on some space, if we down to the nerve, it's coming, this one coming from a map that it's not null homotopic, So what it means that coming from a map like this, I think you know what I mean by this delta. This is the delta distribution. It's also simplicial map. You can think about this is the delta distribution. So if we after down to by this kappa to nerve of Z2, it's become some map of 0 and 1. That map coming from real map, not really a distribution, simplicial distribution map. And this is not null homotopic, then this one is strongly conceptual. Yeah, this one appear like in the side as I explained before in some phase that not involve any classic distribution. Okay. Another point of view, maybe one can see this another point of view that starts from phi that not null homotopic, and we can always find actually such a p, many p's like this that make this diagram commute. So one can find strong conceptual using the not null homotopy maps here. Okay. Okay. Now, actually, the question: what about the opposite direction? Is that characterize every strong conceptual simplicial distribution or not? This is the question. So the answer is not, but we will show how in a specific case it's true. In the case when n is 2 and x is one-dimensional, like one skeleton graph, directed graph. Okay, in this case it's true. It's if and only if. And in order to show this, we will use category theory that behind this delta, behind the outcome, simplicial set. Okay. So let's move to the other direction. Okay, let me define a compository. A compository is actually, it's defined by Flory and Fritz in their paper. It's a simplicial set that equipped it with a composition operation. Like if I have n simplex with a common k simplex phase, I can get some higher order simplex in this order. Okay, like for example, if we have a triangle and other triangle, we have some operation, but they are matched in some age, we will get pyramid. Okay, okay. So this sometimes happens. There is a phenomena. It's really, I like this paper because it's this phenomena happen actually in some cases. Maybe the easiest one. Before this, I want to say that it's not just an operation. Like this operation, it's a good like composition, like satisfy some axiom which give us the associativity and other nice properties. Okay, it's not any composition. But the example, like the trivial example, is the nerve of a category, because the nerve of a category, if we have like something that much, it's exactly defined the upper wall. This is the definition. So it's actually the composition is the identity in this case. But another non-trivial case, when we apply the distribution monad on the nerve of C, this will be also a compository. Okay, that we mean that we have in this one we have we can compose simplex. Okay, when they glue, like we can glue simplex, we can say, yeah. Okay, so delta Z, we back to delta Zn. Actually, delta Zn in general, but we're interested now in delta Z2. Delta Z2 is also a nerve. Maybe we didn't see this before, but it's a nerve of this category, actually. That it's a nerve of this category. So for this reason, D of delta Z2 is compository. Okay, it's compository, and we're going now to use this fact in order to show how to prove the opposite direction. So what I mean here, like if we have distribution and other distribution, we can compose like they are. You remember the dimension, it's 1 plus 1 minus 0. Here they have 0. So it's give me a distribution on the triangle, but we actually down to this one, we can like do the marginal as we did before and got here distribution in one line. So there is composition here. This composition in d of delta z n in general. Okay. So now if we have one skeleton, if the marginal space is one skeleton, like one can say, think about this as directed graph, we can think about simplicial distribution as a category, because from this, like we can compose, because we can compose. We have some distribution here, other distribution, we can compose. So we can take the categories that generated by this. Of course, we also have to think about every distribution that is a distribution from in the opposite side. So in some way, we can get this category. Okay. This in the case when we have one skeleton. Okay. We hope we can generalize this for higher order simplicial sets, but this is a fact. And we have the following proposition that characterizing in this case strongly conceptual. So distribution. So a simplicial distribution is a strongly conceptual if and only if for some vertex, like some object in the category. Vertex now is object in this category. For in some object, there is endomorphism in this category that this is the unique strongly conceptual in this scenario we described before, the simplest scenario. Remember, I come back just a minute. Come back here. You remember this scenario we said when we have circle, like we have unique here, strongly conceptual vertex. So this P is strongly conceptual if and only if there is some endomorphism that is strongly conceptual as a scenario in this like in this circle, okay, as a distribution in this scenario, the circle scenario, okay. So this is actually a strong fact that tell me that we don't have to know everything. We just search about the endomorphism in this category. Yeah, 5 minutes. 5 minutes. Yeah, yeah. Okay. And from this fact we can get the opposite direction. So this is the main result. That in the case we have one skeleton and delta Z2, what I described before, it's if and only. Okay. Like also, if we have strongly conceptual, so it should be come from such a not null homotopic map. So that is it. Right.
Okay.
So, yes, are there any questions for Aziz?
Yes. First, yeah.
Is polytopic had a picture of
The polytope.
Yeah. So how is this in terms of polytope of non-signal empirical models?
Yeah, exactly. Yeah.
It's the same thing.
Yeah.
But then why do you have non-contextual distributions that go all the way up to the edges? Because I thought that
Where?
that polytope,
Here?
yeah, and should the non-contextual distributions.
No, it's just to illustrate the plan. It's not really like a polytope, or just to illustrate. Like you have here in the middle, the non-conceptual one. Also, there is a vertex, the deterministic vertices there is here. It's also vertices. And you have here the conceptuals. Yeah. It's not something really like for some scenario, really. No, it's just, yeah. This one for real scenario.
This is exactly that polytope.
Yeah, I mean, yes. Yeah. All this.
Anyone else? I actually have a question about this one too. This kind of suggests that the subspace of non-contextual distributions is convex. Is that true? Or is that
It's true.
Okay.
Yeah, it's true. Actually, there is a map, there is a convex map that coming from all the global
I see.
which is convex by itself.
I see.
Yeah,
Okay.
so it's like, yeah. So.
Good. Any other questions? No. Then let's
Thank you very much.